So let's think of what kinds of vectors we might want to have in here. Well, it might be good to think of maybe the position vector and maybe its variation. So if we wait a certain amount of time, we'll have a vector delta r, which is the change in position vector over a certain interval of time. Okay. So let's start with the first step. What's the most complicated thing in here? It's this area swept out by the line. How do we express that area in terms of vectors? Well, I've almost given the answer by drawing this picture, right? If I take a sufficiently small amount of time, this grayed region looks like a triangle. So we have to find the area of a triangle. Well, we know how to do that now. So the area is approximately equal to 1/2 of the area of a parallelogram that I could form from these vectors. And the area of a parallelogram is given by the magnitude of a cross product. Okay, so I should say this is the area swept in time delta t. And you should think of delta t as relatively small. I mean, at the scale of a planet, that might still be, a few days, but small compared to the overall trajectory. So now let's remember that the amount by which we moved, delta r, is approximately equal to v times delta t. Okay? I'm just using the definition of a velocity vector. So let's use that. So it's again approximately equal to r cross v magnitude times delta t. I can take out the delta t, which is a scalar. So now what does it mean to say that area is swept at a constant rate? It means this thing is proportional to delta t. So that means, so the law says, in fact, that the length of this cross product r cross v equals constant. Okay. R cross v has constant length. Okay. Any questions about that? No? Yes? Yes, let me try to explain that again. So what I'm claiming is that the length of the cross product r cross v measures the rate at which area is swept by the position vector. I should say with a factor of 2. 1/2 of this length is the rate at which area is swept. How do we see that? Well, let's take a small time interval delta t. In time delta t, our planet moves by v delta t. Okay? So if it moves by v delta t, it means that this triangle up there has two sides. One is the position vector r, the other one is v delta t. So its area is given by 1/2 of the magnitude of a cross product. That's the formula we've seen for the area of a triangle in space. So the area is 1/2 of the cross product r and v delta t, magnitude of a cross product. So to say that the rate at which area is swept is constant means that these two are proportional. Area divided by delta t is constant over time, and so this is constant.